Welcome to This Explainer. Today, we're going to absolutely demystify the hidden backbone of our electrical grids and industrial plants. If you've ever stared at a massive substation and thought, how in the world do engineers decide exactly how the power flows through that maze? Well, you are in the exact right place. We're unpacking an absolutely foundational choice in power system design, the single versus double busbar scheme. Think of your power system kind of like a massive, busy traffic intersection, or, the main water pipe feeding an entire city. If that central shared node fails, boom, the entire plant shuts down. It honestly doesn't matter how robust your edge devices are if the core just collapses. And this is the exact dilemma electrical engineers face every single time they design a new facility. They have to figure out just how much redundancy is strictly necessary, because, as we're going to see, buying your way out of a single point of failure, it is not cheap.
So here's our roadmap for today. We'll start with Part 1, the hardest switchgear, then move right into Part 2, the single busbar scheme. After that, Part 3 covers the double busbar scheme, followed by Part 4, a head-to-head comparison, and we'll wrap up with Part 5, making the right choice.
All right, let's jump right into Part 1, the heart of switchgear.
Now, according to IEEE standards, the bus isn't just a simple copper or aluminum conductor. Far from it. It's really the critical shared node for your feeders and transformers. Literally, one single topology choice here alters your entire operational risk. You see, the practical choice is never just about drawing a neat little one-line diagram on a screen. This decision dictates your outage management, your fault isolation, your operating complexity, and ultimately, your total lifecycle cost. It's a massive, system-level decision that defines exactly how safely you can change operating states in a seriously high-voltage environment. Which brings us to the baseline. Part 2, the single busbar scheme. This scheme brilliantly illustrates the ultimate rule of engineering trade-offs. The single busbar scheme is exactly what it sounds like. You have one common main bus serving all your incomers, feeders, and transformer circuits. The incredibly simple design saves a tremendous amount of money and space. Your protection zones are super straightforward, and you just need fewer panels overall. But, and this is a huge but, its Achilles heel is glaringly obvious. A single bus fault drops absolutely every connected load. Poof, everything goes dark. Plus, if you need to do routine maintenance on that bus, you have to initiate a full facility outage. So in a cost-sensitive environment, this is a brilliant, highly efficient design. But in a mission-critical environment, it's a terrifying liability.
Now you can mitigate this liability a bit by splitting the bus with a sectionalizer breaker. This basically limits the blast radius of a fault. Instead of losing the whole plant, you might just lose half of it. It's often used in industrial settings as a sort of redundancy light to really balance cost and reliability. However, while it definitely helps contain faults, it still doesn't give you full transfer flexibility. You're still ultimately constrained by the limitations of having a single shared pathway.
So, as load criticality rises, that baseline single bus layout inevitably fails to meet our needs. And that brings us to Part 3, the double busbar scheme. By adding a second main bus, what we usually call bus A and bus B, and installing selector disconnectors, complexity essentially buys you freedom. This arrangement actually allows one bus to stay fully energized while the other is isolated for inspection or repair. A fault on one bus doesn't just automatically drop your whole installation anymore. But, as you can guess, the price tag for this flexibility is steep. You need a lot more space, way more disconnectors, and highly disciplined operating procedures to manage the really complex switching sequences. And trust me on this, the physical footprint needed for this can sometimes feel like you're building a whole second facility just to house the backup. But to make this dual system truly work without ever dropping the power supply, you absolutely need a critical piece of equipment. Without it, honestly, having two buses is practically useless for live operations. Enter the bus coupler. It's essentially the ultimate traffic cop of the system. As AB Group notes, it's a dedicated switching device that connects the two buses, enabling controlled transfer between them without any load interruption whatsoever. It gives operators the incredible freedom to manage outages seamlessly. Let's say you want to move a highly critical feeder from bus A over to bus B so you can safely perform maintenance on bus A. Well, the bus coupler is what makes that live transfer possible. It is the exact specific mechanism that transforms a rigid static metal grid into a dynamic, highly resilient power network. Now keep in mind, a full double bus is very different from a main and transfer setup. You'll sometimes see a main and transfer bus used just to keep a circuit alive while its specific breaker is being serviced. In that setup, the transfer bus is really just a temporary maintenance spare. It's kind of like a donut spare tire on your car. A true double busbar scheme, on the other hand, is literally like having dual independent drivetrains. Both buses are fully robust, operationally active, and entirely capable of sharing the facility's load under standard conditions.
All right, it is time for a direct showdown to see what you are really paying for. Let's look at Part 4, head-to-head comparison.
So the really crucial point here is that a single bus minimizes your equipment count, whereas a double bus minimizes your operational constraints. If a fault hits a single bus bar, you lose all circuits, period. But if it hits a double bus bar, you only lose the affected bus. The other one remains totally live for a full load transfer. It's a really stark contrast. The single option is cheaper, simpler, and much more compact. The double option is costlier, definitely larger, and highly complex, but it practically guarantees service continuity. Neither one just wins outright, you know? It entirely depends on what your facility is actually doing day to day.
Which begs the question, how do engineers actually make this call? Let's move to our final section, Part 5, making the right choice.
Engineers follow this exact sequence to ensure the switchgear topology actually satisfies the project reliability needs without completely, destroying the budget. First up, you assess load criticality. Basically, what actually happens if the power dies. Second, you set the reliability target. Can the plant even accept planned shutdowns? Third, you have to calculate the short-circuit fault levels using standards like IEC 60909. Fourth, define your maintenance philosophy. Like, do you need to inspect the bus without shutting down the entire factory? And finally, step 5, evaluate the life cycle economics. As you can probably guess, high continuity requirements inevitably push designs right toward those expensive, customized double bus solutions.
Ultimately, deployment follows consequence, not fashion. Take a data center, which powers cloud computing and AI. It absolutely demands a double bus bar because a single minute of unplanned downtime can cost upwards of $9,000. They require absolute zero downtime. Similarly, a transmission substation running at 220 kilovolts requires maximum flexibility. On the flip side, a small commercial distribution network is incredibly cost-sensitive, which makes a single bus bar the perfect fit. And your average industrial plant, it sits right in the middle, perfectly utilizing that sectionalized single bus we talked about earlier to strike a great balance between cost and reliability.
At the end of the day, single and double bus bar schemes aren't just competing buzzwords. They are two drastically different answers to the exact same engineering problem. So I'll leave you with this thought to evaluate your own infrastructure's resilience. Are you saving a few dollars on capital expenditure today, only to leave your facility completely wide open to catastrophic, irreversible downtime tomorrow? I really hope this explainer helps you map out your next major power project with absolute clarity.